So good morning. Welcome. My name is Chuck Lukaszewski. It was good to meet some of you last night. So a little difficult to do demos to fit a stadium in here. So this will mostly be lecture, but spend a huge amount of time in different kinds of stadiums and arenas and all manner of what we call ultra-high capacity environments over the last 3+ years. And we want to share some of that learning with you today. They're fairly complicated environments, and there's a fair amount of material, so I'm going to move fast, but stop me as we go if you have any questions. So the first thing to be clear on is that the arena stadium environment is basically becoming a extraordinarily complex access network. Not just from a wireless perspective, although typically that's the sort of last mile or last meter or whatever term you want to use in terms of delivering services inside the venue. But there can be coverage expectations, wired or wireless, literally throughout the venue, and we see a proliferation of new types of services. The leagues, the team owners at a professional level and at a collegiate level are thinking about how to fill the seats, right, and how to differentiate the fan experience in the venue from what people can get on television at home, right? And so they want to provide incremental services and other kinds of capabilities in that environment. And from our perspective, a couple of just key points, having done a lot of work in this environment. So the first thing is choice. It is essential that the venue, the operator of the network, whether it's a carrier on behalf of the venue for 3G offload, whether it's the team owner or facility operator themselves, they need to be able to choose whatever applications they want to provide and providers, and it's very fluid, right? A lot of different revenue models, right? Neutral host to single host type thing, and the last point's important as well. We don't believe that there. In fact, we know that there is not such a thing as a one-size-fits-all stadium solution at a systems level, much less at an access point or even an antenna level. We do hear that in the marketplace, but the fact of the matter is you need a toolkit as a wireless architect to be able to come at these facilities and use the right tool for the job. So choice is important. The RF design is crucial. We're going to talk a lot about that. And this concept of orthogonal coverage blankets is something I talked a lot about in terms of minimizing the interference, the self-interference environment. And then as Paul was talking about earlier, we've got a lot of capabilities in the control. We want to, spectrum is precious, airtime is precious, and so we want to minimize unnecessary consumption of that resource. Just real quick, most of my talk is going to be on the RF side of things, but just to kind of give you a sense of the kind of holistic solution that Aruba brings to the table. So from a stadium perspective, obviously access point's pretty straightforward. Our switching solution also is very relevant in the stadium environment. If you think about the offered loads in a venue, right, it's not uncommon. Most venues have less than 100 megabits uplink out of the stadium, right? So, and a lot of them have a DS3 maybe at best. So this is right away it's a sanity check at the door when you begin, independent of whatever applications might be running in the venue. So we're talking about even though it's a complicated access network, the offered loads at any point in time are actually fairly low relative to what we might expect in a large campus, enterprise, or university type environment. So anyway, we've got a comprehensive solution there, and then obviously visibility, being able to see what's happening on the network, guest access, our ClearPath solution for onboarding and classification and profiling of devices, all kind of can work together in these environments. So we really do have a kind of comprehensive package. And then from a carrier perspective, because a lot of the venues right now, the funding mechanism is carrier offload, right? So you've got AT&T or Verizon, or in other countries, this is going on internationally actually, so you might have a Mobile in the Middle East, for example, actually funding the deployment of the stadium.
Do you have any product line of your own for the service gateway, or you're only providing the interface?
We're providing the interface today, yes, yeah. And obviously, when we go global, there's a range of authentication methods, back-end authentication, so we have to, obviously, Whisper is one of those we've supported for a long time. Hotspot 2.0 support is coming. So we're very much at the forefront of being able to integrate into these carrier billing and authorization environments. So what are we dealing with? What are the technical requirements in a ultra-high capacity environment? So just real fast, some of these are self-explanatory, right? Not just uncontrolled, not just heterogeneous, but uncontrolled. That's really the key term, right? We don't own them, we don't know what's on them, and we don't know what capabilities they have. We'll talk about the per user bandwidth quite a bit in a few slides. I think this came up earlier, the question about, not all iPads are alike, not all, what about one stream versus 3 streams? So an expectation setting exercise we have to go through with customers is, the marketplace has an expectation around 300 megabits per second, right, which is transitioning to 450. But that's just a potential number, and it's completely dependent on the capability of the client. So most tablets and smartphones today are 1x1 HT20 devices, which limits them to a maximum PHY rate of 65 megabits per second, right? And so this is a significant capacity impacting number, right? They're going to take longer to get off the air. It's going to cap the amount of good put that we can deliver. But it's also helpful because it allows us to more accurately or more efficiently allocate the spectrum. We don't need to tie up bonded channels, for example, if we know that our clients don't require them. So I want to clear up some common misconceptions. So I use a bus metaphor quite a lot. And there's a tendency when I look at some stadium designs that we encounter that have been done, I see this idea that basically APs are like buses, and if I need to get a lot of people to my event, I just order up however many buses I need to carry that number of people, right? And it's a little more complicated than that. So what people don't remember is that the real limiting factor is the number of lanes on the highway, right? So, and in 2.4, I'm sure everybody, basically I consider, I think they ought to call it the iPhone 5G, 5 gig. We're very, very happy about the news from Apple this week. But most of these networks have been designed to carry the bulk of the traffic in 2.4. And it's common to see a take rate requirement in the venue space between 20 and 25% of concurrent of seating capacity. And you can get into, is it associated, is it concurrent, and so on. But most of those are going to hit on 2.4 historically, right? Now we're designing networks for both, but the key point is, if you're stuck in line, you're not going to be getting the kind of performance that you expect. So getting this across to customers is quite a challenge.
Is that the number you work off then? Because I've tried to find stadium numbers in the past. Let's say you've got a stadium of 10,000.
Mm-hmm.
Is 20-25% a number? I mean, it could vary by venue and depending on if it's a sports stadium or music or whatever.
Yes.
But is 20-25% a number?
That's a number that we hear from carriers quite a bit,
okay.
And it seems to have made its way to the venue operators. So that pretty common number today. We're thinking, we're doing also. It's a good segue, right? In terms of what the limits of the technology are today with what the radios can do on the client side, it's actually a pretty good value. We're not satisfied with that, actually. So we're doing work to get way past 20%, right? Because the number of devices in the environment is only increasing.
Yeah.
Right. So that's a segue to, okay, well, what's actually achievable? So we put out I know you're familiar. I used to run the validated reference design program, and one of the VRDs we put out a few years ago is the high density. This is the very first.
Yeah, and it's still the best one out there. So props to you.
Thank you. We put a lot of work into that book. So here's a chart. You've seen a version of this chart in the book, but not this chart. So we basically took the live data. For those that are watching on the internet, just a quick, the way you read this chart is that we've got clients across the bottom and increasing starting from 10 going out to 150. And then this is a per client throughput chart. It's not an aggregate chart. And what you're seeing is that the per client throughput decreases as we add clients to the mix. And the colors just represent different combinations of PHY types, so legacy versus 11N mixes. So we expect that this is going to go down because the more clients we add, as you saw earlier, you know, the pie is only so big and the slices have to get smaller, essentially, as we add clients. And there's also a contention premium in the air, right? As we add clients, we're going to lose channel space to contention and just inefficiencies. So normally, so these are actually real results out to 50. We've extrapolated those results out to 150, and we do get questions from carriers, for example, a lot of times about, well, why can't I put, you know, 200, 500 users on the radio?
So you're saying you're talking about 50 active sessions.
50 concurrent transmitting sessions. Yes.
Not necessarily 50 associations.
Correct, yeah. And our best practice recommendation, I think we say it in the guide, is we generally recommend a 3-to-1 ratio of concurrent to associated. And I'll walk through that methodology in a minute. But if these were all concurrent, you would expect to see at best, right? And these are extrapolated results, lab conditions, single room. It is all with real client. These were with real clients, so there is contention happening, but there's no ACI, there's no coach comm system on the air, there's no Goodyear blimp broadcast, you know, taking out channels. So, you know, we would derate from these numbers to something that we would actually plan to deploy, right?
Is all this one spatial stream, the 5 times?
These are 2 spatial stream results, so your iPad results will be half this, right? For example. So anyway, the point is to set, we need a quantitative basis to be able to have this discussion with a customer about what can you actually expect, right? And that's one of the reasons we published the book, because customers really didn't know what was possible. And, you know, so of course you're going to ask for the moon in that case, right? And so we wanted to be able to kind of put it on a quantitative footing. So just a little bit about interference. So we deal with ACI and CCI, adjacent channel and co-channel interference in any kind of high density environment. And the VRD is built around auditoriums, but if you understand the design rules that are in that book, you can apply them literally anywhere, right? So adjacent channel interference, the mechanism is, so the clear channel assessment in Wi-Fi has 2 components. There's a physical component and a virtual component. The physical component is based on something called the energy detect threshold, which quite a few are familiar with, but basically if we're at office type ranges, few meters between stations, no big deal. But if we're in stadium type environments, right, and we're down to just a meter or people sitting next to each other, ACI actually, the energy threshold can actually start to play an active role in the performance of the system. And what we're showing here is three pairs of AP clients, one on 36, one on channel 40, one on channel 44. We call this the victim in the middle. And assuming that AP1 and AP3 have their respective channels, and this pair wants to transmit, can he get on the air? And because you can see the bottom of the spectral mask skirt is above the CCA threshold, the radios here are going to come back, the Macs are going to come back and report the channel is busy, right? So he won't get on the air. And you can actually see this, and you can set up this test and do it. It's actually quite interesting to do. So that's adjacent channel interference, and it's quite real. These are some test results, again, that are in the VRD, but if we have 50 feet of separation, we have basically full performance, meaning that the lines line up. But as we start to decrease the distance to 25 feet and actually co-locate the victim with the other interfering APs, we actually start to see a significant reduction in performance. So it's a real phenomenon. The other issue that we deal with is co-channel interference, and some of you may have seen this diagram. We've had it in a couple of different documents that we've published. Basically, Wi-Fi works by reusing the same channel at intervals, just like the cellular network does, right? And so if two channels two APs are on the same channel, and you've got two different clients and they can hear each other, that's co-channel interference. It's not, some people that are new to Wi-Fi sometimes think that it's interference in the sense of a microwave oven type of interference. It's more coordinated than that. It means that the radios can actually decode each other's transmissions, and they're aware that the medium is in use. What most people don't know is the mechanism of the interference and the interference radius that occurs due to that. And so if we get out our CWNP documentation, we can quickly see that the second part of the carrier sense is the virtual carrier sense. And the way that this works is at the MAC and the PHY layer, there is a preamble which is transmitted at, by standard, the lowest OFDM rate. And the problem with the lowest OFDM rate is by design, it's decodable with a very small amount of signal, right? And because RF is an exponential decay, it falls off very fast here, but then it decays very slowly. And just to kind of put that into context, you can actually do this thought exercise. So if I'm engineering for a neg65 cell edge and 25 SNR, it's quite easy to determine my interference radius from a CCI perspective for that, for the preamble, right? We know that every 6 dB is, a halving or a doubling of distance, right? So I just do my 6s, and I'm out to over 250 meters in free space for an interference radius for the CCI mechanism, right? So obviously, stadium's a lot smaller than 250 meters. So these are the kinds of challenges that we deal with, and this is why the RF design is such a critical topic. So how do we plan for it? So the basic process that we recommend kind of goes like this. We start on the top with the how many subscribers, what's the take rate, right, that we're expected to design for, how many channels, how much capacity are we going to count on per channel. A little bit here, we'll talk about associated versus concurrent capacity, and then fine tune it. So the number of devices.
Could you go back a slide? Just
Sure.
There was a bullet point, the last one. What did you mean by partial solutions? As in multiple vendors are touching the same RF?
Meaning that it's important to do it systematically. Our experience is we want to have one system in the venue. If we have a couple of different systems with different RF designs, they more than likely are going to step on each other. It's important to have if we're going to deploy a high capacity, we want to be the system. And we also want to migrate other users to that system, right, or other classes of traffic, video, or what have you, from a frequency planning perspective. But we also don't want other Wi-Fi systems, right, contending for the air. So device count's pretty straightforward. So if we move on to channel count, obviously this is going to vary by country. And so one of the things that's been fun about working at Aruba is getting to work in a lot of different countries and getting familiar with the regulatory regimes that are different. And you can get a sense of just how different, on a day-to-day basis. In China, I've got 5 channels to work with in all of the 5 gig band, right? Here in the US, we used to have 24. We're down to 20. A lot of people don't know that, but we actually lost 4 channels in the middle of the DFS band due to some changes in FCC rules because of non-compliant integrators doing things that they weren't supposed to do. So a lot of different variety, and of course, so the starting point is how many channels do I have to work with? Am I going to use DFS channels? Our recommendation would be yes in this type of environment. The downside of not having the potential cost of using a DFS channel is outweighed by the need to get people on the air. Basically, it's a very simple cost-benefit trade-off.
Chuck, how do you deal with the devices that can't actually use the DFS channels?
So the expectation is that they're going to find an access point that is on a channel that they can speak to, and it could result in suboptimal performance for some clients. This is one of those sort of good of the menu over the...
Do you see a particular class of clients that you know can't use them as opposed to okay?
I have not done a whole lot of analytics about that. Usually we're looking at sort of aggregated game day type statistics. We don't take it down. This is probably part of the problem with the uncontrolled environment. It's really difficult to do controlled tests. So we've done things like, do some sort of raffle or giveaway to get 300 students to come into a university for, half a day so that we can do scaling tests. And and in that case, we get control over the outcome. But it turns out that those results really until you fill that venue up, the data is really no good. And of course, if we fill it up, we can't control the results. So I don't have a clear answer to the question that you're asking. But our sense, in terms of what we're measured on, which is the aggregate throughput and the overall, basically the complaints that the operator hears, that has not come up as a...
So are you generally recommending for a stadium where it's going to be mostly smartphones, is the recommendation to enable those Uni 2E channels?
Yes, the recommendation is absolutely...
So you get those extra double channels?
Yep.
Most won't be used anyway, they're gonna be on 2.4.
Yeah, and honestly, we don't see, I rarely ever see a radar event, even in maritime environments. I do a lot of outdoor work, and the chipsets today are pretty good about, we're a long way from the first gen chipsets where kind of the DFS requirements were imposed retroactively right after on the industry. So the first chipsets had issues with false positives and so on, but really we don't have to be that concerned about that issue going forward. And again, as I say, even if I have a hole punched in my channel plan in this section, it's still the lesser evil, and the system will compensate.
There's not many, obviously, smartphones with 5 gig, but the Samsungs, there are quite a few Samsungs that make up, the small percentage.
Mm-hmm.
And from what I've seen, a lot of those don't even support, like mine doesn't support Uni 3
Mm-hmm.
in Australia, but in the UK, I think it only supports, whatever.
Yeah.
But in the UK, I think it only supports Uni 1, and so you've not only got the gap in Uni 2E, but you're not even getting the end of the band.
Yeah.
So it's early days. So I guess it'll be interesting with the iPhone 5 as to what bands it actually supports, because you've got even larger holes in your gaps in your coverage.
Yeah. So you can pretty much be assured. Again, these are very small spaces. There will be signal on a channel that device can associate with. It's really just a question of what the rate of performance is that it's going to get.
And in this use case, it doesn't really matter, like you said. I mean, if it's kind of deprecated, but in other use cases, like in a hospital or something like that,
Right.
different story. Different story.
Different story. So just to keep it moving, I know we're tight on time. So we can start to then take the two metrics, right? The device count and my channel count, and my next decision is, okay, how many users am I going to put on a radio? And when I say user, I mean concurrent user. That's usually the way that's the harder decision, right? So this chart, again, it's in the VRD, but basically this is just showing us, with no reuse, right, how many I can get at different channel counts, and I can, depending on my environment, I can come here and then that gives me a sense of what I can do in a smaller venue. In a stadium, of course, we're committed to channel reuse, right? And so now the question is, well, how do we achieve reuse? Because as we saw earlier, the interference radius is actually quite substantial. So that is the segue to RF design. So there are basically 3 ways you can cover any type of space. So I use the term coverage strategy to just talk about what method am I going to use to apply. So we have overhead coverage, we have side coverage with or without external antennas, and we have one that we like to talk about a lot is underfloor or on-floor mounting. We do it both ways, and the idea is to have very small sort of picocells. And this is a concept that a lot of people are sort of new to, and there's an appendix in the VRD that talks about this. And then we have a new VRD, I don't know if you've seen it, for outdoor MIMO wireless networks. It's the first reference design for MIMO outdoor. It's a great book. You should take a look at it. And there's an appendix in that VRD, and I think we're going to publish a link to it. There'll be links for all these presentations, but there's a appendix specifically on stadium use case, how to design for stadiums. But the Picocell environment is kind of a little complex in the sense that we now have to be concerned about, if interference radii and so on. And I'm not going to get deeply into this. My point is just that there is engineering that has been done and a significant amount of testing work that's been done, because people hear, oh, well, going through the concrete, how's that going to work and so on. It works actually surprisingly well. It does depend on the facility. We get pretty good results in 2.4 across the board. We have seen some stadiums where the 5 gig just wasn't going to make it.
New facilities are a problem because of the moisture in the concrete. The new facility, newly built facilities are a problem.
Yes, definitely the concrete. So the older concrete is actually much better than the newer concrete to work with for sure. Also, indoor versus outdoor makes a difference. So because there's a lot less volume in the material in the indoor arenas. So, it's not we definitely don't. We use a lot of methods, as you're about to see. This is one tool in the toolkit to produce a complete system, and that's sort of the key message. Again, you could do the link budget analysis, and we've done all this, and the book goes into it in a fair amount of detail. Again, my point is simply that there's engineering behind this concept. So I'm going to walk you through an example of this. We'll talk about Turner Field in Atlanta in just a second, but before I get to that, I want to just close out. So it's not just about the RF design. The controller actually plays an important role in the performance of the system. And so we have a number of features that are really essential. And you've heard about several of them this morning. These are features that are useful in different cases, different use cases, but we leverage here as well. So obviously, channel distribution is important. Client distribution is important. Power control is important. I want to call attention to this last one. Paul talked about and Bala talked about eliminating unnecessary traffic on the air and controlling unnecessary traffic. So this is extraordinarily important. I'd say even more important in a stadium environment than it is in a classroom type of facility. And with the firewall capabilities, with the rate optimization capabilities, a lot of the innovations that have happened at a PHY layer here at Aruba, we're able to actually do. We feel that we can get more out of the air with a controller-based design given the same RF approach.
Have you had any experience with IPv6 deployments in the stadiums?
No, it's not been a requirement yet. We do a lot of V6 around here, but not.
No, but in the high density it will make more impact. Right?
It will certainly make an impact, yes. So we talked about the cell size reduction earlier. Paul mentioned it, and one of you had a question about how it worked. So one of the other features that isn't listed there is this CSR feature. We used to call it this receive sensitivity tuning-based channel reuse. And in addition to having a more memorable name, it's had a lot of enhancements to it now. But basically, the way that it works, we also call it the earmuff feature. So if you're maybe newer to RF, basically think about just making yourself selectively deaf to transmissions that are far away, right? And that has the effect of pulling in the effective edge of the cell. And the way that we do that is we reach down into the radio, and the radio chipset manufacturers give us the ability to manipulate certain things at a fairly low level, one of which is the receive sensitivity threshold of the device. Normally that's set way down, right, because we want to pick everything up. But we actually have the ability to bring that level up. And so anything that's below that level will never be decoded, right? Even if there's sufficient SNR, it's going to be just treated, it's going to be thrown out by it won't even begin the decoding process, the demodulation process. So you can see immediately how this is really helpful in a stadium environment, because I don't want my APs blocking on other APs in other parts of the venue. Even though clients are such an important, they dominate the problem, in a certain sense, the APs have significant influence on the result, right? And then I won't Paul's already talked about these. You've seen these discussed. We do manage the data rate environment. We typically stay away from. It's the usual sort of best practice in a tricky environment, right? So we're going to cut out the low rates, cut out maybe the top rate, and in general, we tell customers to, the B devices have to go, right?
Do you see most of these are in these venues are not really mobile? Most of them are static, even though they're on mobile devices. Most of the
people aren't walking around.
Yeah, there's not a lot of roaming activity. We don't have. I've never had a customer stipulate a roaming requirement.
Yeah.
Do you have customers that have like roaming POS stations, where they can take payment over the wireless network for popcorn or whatever sales in the stands?
Those exist, but typically it's never bubbled up as a technical requirement, and the system would handle it. But in terms of, we're not doing L3 mobility or anything along that line. It just that'll be a very nice problem to have at some point as we see increased pervasiveness of these.
Did this experience change any feedback into how ARM is doing its algorithm?
Very much, very much. Yeah.
One more quick thing. Have you noticed it's better to use in these high density scenarios 20 megahertz channels instead of 40?
Thank you. I forgot to talk about this. We didn't have a lot of time, so I had to. This deck is like 150 slides, so picking and choosing was challenging. Yeah. Absolutely. This is not so controversial a recommendation today, I think, as it was when I wrote the high density VRD a couple of years ago. That we're the first vendor to take a position that you should not use bonded channels in a high density environment, and I think pretty much everyone agrees today in terms of documentation I've seen from other vendors. There's two reasons for it. The first is, a lot of devices are not capable of bonded operation, right? So the iPads, most smartphones, we already said that they're 1x1 HT20 devices. So why would I allocate my spectrum inefficiently for devices that really can't use those devices? So that's the first reason. But the second reason is, it's actually fairly easy to demonstrate that you can get more performance, you can get more throughput from from an unbonded environment. And the kind of the thought experiment I described to people is, if I take 100 clients and put them on one access point with a bonded channel, right, so 40 megahertz of spectrum, I will get less throughput than if I take those same 100 clients and break them into two groups of 50 and put each of them on a 20 meg channel and two APs. Right? It's quite easy. You can do this demonstration yourself. It's very simple. And the reason is that fundamentally it's an interrupt and a phi layer event problem. Right? It's the same issue with having more gates to get into the stadium, right, or more lanes on the freeway. The more I can parallelize the access to the medium, and there's an argument to be made that if the medium were efficiently allocated and the clients were using large frames and so on and so forth, that it would actually be better the other way. But what we see in practice when we actually set up that test and we do it is that we get a lot more from the two-channel approach.
Yeah, maybe in a greenfield environment you could get better, but that's, who's ever seen the greenfield environment?
Exactly.
Most stadiums have green.
Yeah. So let me keep it moving. I've said a couple of times that we want to take a systems approach to a venue, and I've said that we want to decrease, we want to be mindful of self-interference. So I see a lot of designs that are what I call kind of the circular RF firing squad, where we just take a ring of, APs with high gain antennas and we point them all at each other, right? With some aim down at the field, but the side lobe and Wi-Fi, the antennas that Wi-Fi vendors sell are quite a bit different than the ones that the cellular vendors use, right? And they're not nearly as precise in terms of the roll-off of the signal edges and so on. So we do get a fair amount of bleed in that environment. So that's just really a non-productive approach. So at Turner, we use 3 different layers, and this is a great example. And I'll just, to make this a little easier, I'll jump to the visual. So I call this the up and out design. So we do the field coverage on the bottom with the high gain antenna, with a fairly steep down angle, right? So we're aiming at row 10, right? Again, we're gonna pick it up over here, but I want to limit, right? If I can be 10 dB down or 15 dB down over here because of my mechanical tilt here, that's going to pay dividends, right? Especially if then I can combine it with cell size reduction. The next layer, we're actually covering the suites and the 200s from here shooting back. So I actually cover the suites from the outside, shoot through the suite, and I cover the hall behind it from the outside. We do that every day indoors, so why wouldn't that work outdoors? And if you look at the side lobe and the front to back, just the rear lobe patterns, it's actually quite good. When we do that, we can see almost nothing from this blanket down here. And then the third layer is up. So we want to be orthogonal to the other two layers, and this is where we use the Pico design. So again, each of these is a tool in the toolkit that you want to use to achieve a system of coverage.
Do you use any additional absorption material for the back lobes?
No. No.
I was in that seat right there a couple months ago.
So, and here it is at scale. Some of you know about our 3D modeling tool. So let me just show you some photographs. So here's the lower blanket, and this is a 3-panel array. There's a MIMO 5 gig antenna in the middle, and we just we didn't have a MIMO 2.4 antenna until literally just this month. So this will be.
I was wondering what antennas were on there. We're not.
Yeah. So there are four, in this level we're using a 30 by 30 pattern, 14 dBi gain.
So these are Aruba antennas.
Huh?
Are these Aruba antennas?
These are Aruba antennas. We have a new antenna array for stadiums that are smaller than these. They're both MIMO, so it'll be two antennas. The 5 gig is about that big, and the 2.4 is about this big. We do not believe, some people think that you can have a single antenna to do both jobs. We're just not a believer in it. As you can see from the approach I've just described, we want to be able to we want the wireless engineer to have the flexibility to use the right tool for the job, and there is no such thing as a one-size-fits-all.
What is the distance between, let's say, 2.4 antennas?
You're probably, well, you're one antenna apart. This is half a meter, less than half a meter. Huh?
Do you find this enough?
Yes. Well, if you think about in a MIMO antenna, those elements are inside the same radome. So clear this.
Just close it.
Yeah, just did cancel. So so this is a MIMO 5 gig antenna in the middle, right? And all the MIMO multipolarization arrays have multiple elements within
One radome.
Yeah, it certainly has a coupling effect. I mean, one area that antenna designers spend a lot of time on is the spacing and arrangement of the elements, because there is a coupling effect, for sure. Although the coupling effect is mitigated by the polarization differences, right? So, and you can see that in the pattern plots.
This was the 175?
Yeah, this is a 175, and we see a lot of painted APs and antennas in the stadium. So this is the lower blanket. Here's the Pico blanket. Again, 175. Now I'm using a different antenna. I'm using a 60 by 60 pattern with a 7 to 8 dBi of gain. It's a dual band antenna, and we slope the antenna to match the. It's common sense, but we have tested it at several different orientations, and this in fact is the one that produces the best cell above it. So that's an outdoor arena, and then just the last example is we also work indoors. A lot of there are thousands of indoor arenas around the world, and if anything, these are more difficult than outdoor. The minute we put a roof over the top, I completely change the RF environment, and you can really start to see some of the propagation effects that I was talking about. We did a test actually here where we had an AP up in there's 3 rows of suites in this arena, and we had an AP up in the roof above the ceiling tile on this side at center court, and we went over here to the other suite on the directly opposite side, and we were able to pass 10 mega traffic on an iOS device, right? So the propagation and co-channel issues are really quite significant. So basically, we use the same, we take a similar approach. In this case, here's some numbers about how we came up with the design. So we recommend the AP130 series for, that's our default high density access point. It's got the most memory and the most CPU power of any of our access points. We don't really need the 3-stream component, although that will give us receive gain, right, from an MRC perspective if we need it. But really what we want is the ability to support all those clients. So this is just some of the math, right? And again, in this case, we actually designed it for closer to 50% across both bands.
Go Bulls.
25% on one band, 25% on the other. So here's a view of the AP placements. And this whole most of this network is Pico. So it's 135s under the concrete coming up. And did I keep the, yeah, so here's, just to kind of drive the point home. So here's an air magnet, first level, filtered at neg 55 and neg 60. And I don't have the 5 gig results on here, but they're similar, right? They're shifted just 5 dB, but so we get very good carry through the concrete in this type of facility. And it makes a huge difference because ultimately what we find, and Keith and I talked a little bit about this at dinner last night, really it comes down to an SNR problem. These clients, the smartphones, the tablets really like high SNRs, and we can actually overcome to a degree things like MiFi devices and so on. If we have a lot of very hot cells, very small but very hot cells, we're able to create an environment that client is very happy in, right? And we can, at the same time, sort of reduce the effect of some of these other interference sources.
How many APs were needed to cover, say, the stadium or even that portion?
I think this was, we said 88 on here.
And what's the transmit output power?
Just in the bowl,
What is that?
right? And then there are going to be APs around the concourses.
Sure.
Yeah.
What's the transmit output power of these?
We are generally running at close to full power. Again, we found that we started at low power, but we have found that the clients actually perform better with more power than less, believe it or not.
Yeah, it's more confident there.
Did you try the orthogonal technique here?
We did not. The arenas are trickier in that regard because I don't want, if you set up an AP at center court, you can pick that AP up everywhere. I mean, you can go to the halls behind the bleachers and pick it up, right? So we have these are much smaller environments. If you just dump one of these on Google Earth, and compare it, right, and then going to like an indie track is a whole nother, right, level of scale. But in this case, we need the structure to be attenuating those signals as much as possible, while still somehow delivering 20 SNR in each of those cells. Right. So the structure is our friend. Right. So that's it for my comments. Any other questions?
What APs can you change that receive sensitivity threshold result? It's now in the whole portfolio?
It's across the Aruba OS line. It's all similar driver stack. Yeah. Great, thank you very much.
Thank you.
Thanks, Chuck.